This is Mr. Martin. This video is going to cover part 2 of the first day of section 6.3. We're going to talk about vector operations. So in general, we have two basic vector operations. We're going to have scalar multiplication, which I'll talk about in a second, and then we'll have vector addition. So let's start with scalar multiplication. A scalar multiple of vector v is given by c times v, where c is some real scalar. So you can see in our picture here, we start with our vector v, and then when I multiply it by these scalar numbers, so a half and 2, -1, -3 halves, it either makes it longer or shorter, or could even flip its direction based on whether that scalar is negative or not. So a half v makes it half as long, 2v makes it twice as long, and then if I make it negative v, it flips it in the other direction. Notice that our arrow now goes in this direction. Or -3 halves, it flips it and makes it 1.5 times longer. So that's a scalar multiple. And then for vector addition can correspond to combined or net effects. So if v and w are force vectors, you may have learned about that in physics, so this is directly related to that. The resultant, so when I say the resultant, and you see this in the directions of a problem, it's important that you understand what that word means. The resultant is basically the addition of two vectors. When I add these two forces together, what is the result of those vectors being added together? Okay, the resultant of vector v plus w represents the net force, and we'll talk a lot about net force in some application problems. All right, and typically I don't talk about subtraction of vectors. I always change it to addition of the opposite because it's a little bit easier to visualize. So if I am doing v minus w, I'll change w to the opposite, right? So we know the opposite has the same length, it's just pointing in the opposite direction, and then I'll add them together. Okay, so notice that we changed subtraction of vectors into addition of the opposite. All right, so in physics, you may have learned the tip-to-tail method for finding the resultant or the sum of vectors. And that is a perfectly acceptable method, and sometimes I'll use that, and sometimes I'll use this other method called the parallelogram law. So basically what we do is we'll take each vector and we'll draw it from the same starting point. Okay, so then I have this red vector A and this red vector B. And then what we do is we use these two vectors that start at this red point as the sides of a parallelogram, and then we just complete the parallelogram. So here's the side parallel to vector A, and here's the side parallel to vector B, and I end up with this parallelogram here, this red and blue parallelogram, and then the resultant is going to be that diagonal from the start to the other side of the parallelogram. So basically that diagonal of the parallelogram that starts where the two vectors started. Okay? So the diagonal of the parallelogram is the sum of the vectors. Okay? And if you want to do tip-to-tail, you can. This is just another method that I wanted to mention to you guys. All right, so go ahead and look through these vector properties. Really, they're very similar to properties of algebra that you know, and they're pretty intuitive. And if you have any questions about those, make sure that you ask me. So let's take a look at some examples. So we're going to let vector u be 1, 2, and v is going to be 3, 4. And we're going to find each of the following resultants of these vectors. So for A and B, we're going to sketch a geometric interpretation in addition to the analytical method. So let's start with our picture. So I'm just going to draw a little sketch here. So let's make vector u is 1, 2. So let's put that about here. Let's draw in some hash marks here. And vector v is 3, 4. So let's put that in orange. So 3, 4 is going to be right about here. Zoom in a little bit here. All right, so I'm just going to use the parallelogram method. So I'm going to draw a side parallel to the orange one that goes this way. And I'm going to draw another side parallel to the red one. That's not very good. Let's see if I can move all this. All right, well, we'll keep going. So this one's hard because these vectors aren't very far off from each other. Yeah, this is not a great picture here. So there's that one, and then here's this one. And then our resultant is going to be this diagonal here. So again, if you want to use the tip to tail. Okay, and with a little bit more accurate drawing, you could just pick off what this point is over here and figure out what this is. So now let's do it algebraically. So u plus v, so we're going to have 1, 2 plus 3, 4. So that's going to be 1 plus 3 is 4, and 2 plus 4 is 6. So we have 4, 6. Now, remember that this is called component form, all right? And component form always starts from the origin, and we like that. We're going to talk about another form, which is just a different way to write the answer. It's called standard unit vector form. But just want to give you a little preview there. All right, so let's do part B. So again, let's make a sketch here. See if I can do a little bit better of a job. So we're going to do u minus v. So really I'm going to do u plus the opposite of v. So u again is 1, 2. So let's put that in red again. And the opposite of v is going to be negative 3, negative 4. So negative 3, negative 4. So that's going to be right about there. And again, the slope of these, or the direction, is not very different for these, so it's kind of hard to tell. And then if I finish my parallelogram here, so let's draw in parallel to the red vector, and then parallel to the orange vector, and then we'll get our purple vector here that looks something like this. So this looks like negative 2, negative 1. Let's see how close my picture was here. So now I have 1, 2 plus the opposite of v, so that's going to be negative 3, negative 4. So I end up with 1 minus 3 is negative 2, and 2 minus plus negative 4 is negative 2. So I was a little bit off there, but not too bad. And then that would be our resultant of those two vectors. All right, let's go on to part C. If you want to try this on your own, feel free to pause the video, and then you can check out the solution when you come back. So I'm going to start with 2u. So that's just going to be 2 times 1, 2. So that's going to be 2, 4. And then I'm going to do the opposite of 3v. And then I can just add these. Then I can just do 2u plus the opposite of 3v. So the opposite of 3v is going to be negative 3 times 3, 4. So that's going to give us negative 9, negative 12. And then I'm just going to add these two together. So 2u plus the opposite of 3v is going to equal 2, 4 plus negative 9, negative 12. So 2 minus 9 is negative 7, and 4 minus 12 is negative 8. All right, and you can graph this too. It's just going to be, you know, you're going to have to double u, and you're going to have to triple v and flip it in the opposite direction. But this is sufficient for this. All right, so next we're going to talk about linear combination. So for linear combination, we're going to be using these two standard unit vectors. So when I talk about the word unit, we're talking about something with a length of 1. Okay? So if I look at these two vectors here, I've got I, which is 1, 0. So we'll make this one, we'll make this one. So I is 1, 0, so this is vector I, and j is 0, 1, so that's this vector, j. Okay, so these are standard unit vectors. I is a 1 unit vector along the x-axis, and j is a 1 unit vector along the y-axis. And what we like to do with these is we like to use these to represent vectors as a linear combination of standard unit vectors. So all of this stuff here, it looks sort of confusing. We're going to take the x component and y component, and we're going to multiply it by the standard unit vectors, and we end up with v1i plus v2j. So let's take a look. It's not as complicated as it makes it look. Let's just take a look at an example of if I had a vector, let's say 3, 4, and I wanted to write this in standard unit vector form, all I need to do is write 3i plus 4j. And really, it's just different ways to write the same thing. So this is 3 unit vectors that go in the x direction and 4 unit vectors that go in the y direction. And again, it's just a different way to write it. So personally, anytime I'm given problems in standard unit vector form, I'll usually write it in component form and then convert it back at the end, because for me it's just easier to work it out. So keep in mind, if problem given in standard unit vector form, answer should also be in standard unit vector form. Okay, so you want to be consistent here. Make sure that your answer is in the same form as the information given to you in the problem. All right, that doesn't look so good. Okay, so let's go ahead and take a look at an example. We're going to find 2u minus 3v. So, and I'm going to go ahead and rewrite these vectors in component form because, again, I prefer doing it that way. So u is going to be 1, 1. I'm just taking this and converting it to component form. And v is going to be 5, negative 3. All right, and I want to find 2u minus 3v. So 2u, I always like to write this stuff out so I don't make silly mistakes, is going to be 2, 2. I'm just multiplying this one by 2. And then I'm going to do negative 3v. so that I can just add these two together. So negative 3 times 5 is negative 15, and negative 3 times negative 3 is 9, and then 2u plus negative 3v. So I have 2 plus negative 15 and 2 plus 9. Okay, so if I do negative 3v here, then I don't have to worry about mixing up any signs, positives and negatives. All right, and then we'll just simplify. So I have negative 13 and 11. All right, now finally, shouldn't box that answer. Since our problem was given in standard unit vector form, we want to convert it back. So our final answer is going to be negative 13i plus 11j. All right, that one we'll put a box around. All right, if the problem is given in standard unit vector form, answer should also be in standard unit vector form, even though we completed it using component form. All right, so go ahead and try this problem, and go ahead and pause the video and try this problem, and then when you restart the video, the solution will be there for you. And then if you have any questions, make sure you ask. So pause now, try the problem, and then restart the video when you're finished. All right, welcome back. Here's the solution. So I like to write out a lot of the steps because otherwise I find I make silly mistakes. So the first thing that I did was I rewrote all of my vectors in component form because I prefer to work that way, and then I just converted at the end back to standard unit vector form since that's how it was given. So, and then if there's other quantities inside of this that we need to find, like the 2v and the 6w, I like to find those. So here's negative 2v, here's negative 6w, and then I can just plug everything in that I need. So I have 3 times the quantity of u plus the opposite of 2v, and then here's plus the opposite of 6w, and then I just go through and simplify using order of operations. And then your final answer should be 9i minus 18j. If you didn't get that, see if you can find your mistake, and if you can't, reach out for some help. And that'll be the end of this video, and we will see you next time.